Okay, good afternoon, everyone. Today is a good day for me. Today is Cliff Yu's exit seminar from his PhD. I've known Cliff since 2013. He did a master's with me when I was down south. We worked on a mouthfeel of Merlot under irrigation deficits and solar radiation intrusion into the canopy. Then we switched gears using fundamental science, combining it with proximal sensing, still working on the water relationships of plants. So he studied a great deal about proximal sensing of soil apparent electrical conductivity with soil plant water relationships. And he used this information to provide direction in delineating functional homogeneous zones in vineyards. So far, Cliff put out close to 8 papers. We have one more that's ready to be submitted. So I think he's done quite well, averaging about 2 papers a year from the lab. So I'll turn it over to Cliff, and then he can explain to us what he has done so far for his PhD.
Okay, thank you, Con. Hi, everybody. This is Cliff. I'm a graduating PhD candidate from Horticulture and Agronomy graduate group. And today I'm going to share with you my study for the past few years with all of you. And the title is Proximal Soil Apparent Electrical Conductivity Sensing Provides Soil Plant Water Relationships and Direction in Delineating Functional Homogeneous Zones in Vineyards. So it's a long title. So let's cut to the chase. Let's start it. As many of we know that the vineyard systems are not spatially uniform because of the variability in site topography and soil characteristics, and the cultural practices in commercial vineyards are usually applied in a uniform manner without taking into account this specific condition in each section or each individual vine, which doesn't help to homogenize the vineyard productivity or quality. On the contrary, these practices sometimes could exacerbate this variability spatially. Also, to monitor and to manage this variability spatially, like taking soil samples and measuring plants at field scale, is really challenging. And this makes it nearly impossible to individualize each of the existing spatial variability for making further management decisions. So with recent advancement in data science and sensor technologies, proximal soil sensing, specifically electromagnetic induction, EMI, has been increasingly studied and used in viticulture systems. They are beneficial due to their non-destructive and prompt attributes to cover almost the whole vineyard when you use these technologies. So it becomes more relevant in the real world setting. And in the Californian summer, which is dry and hot, everybody knows that the water is from the soil, not from the sky. So when we track back all these resources for spatial variability, being under the same climate condition and same topography, these processes involved in the soil plant continuum and the atmosphere system are strictly influenced by soil. The soil plant water relations are extremely critical based on this, since water will always determine plant growth and development. This is where the soil proximal sensing will be useful in our vineyards. So the soil apparent electrical conductivity, ECA, is an integrated parameter can be used to assess many soil variables, including soil texture, soil moisture content, salinity, or soil temperature. So it has the potential to spatially predict plant water status and further plant physiology, including berry chemistry. But current studies do not provide enough information of spatial variability observed in soil ECA and how it is translated into the variability in plant water status at field scale in wine-grade vineyards. The relationships between ECA and plant water status was not thoroughly studied yet. Like mentioned above, as an integrated parameter, researchers did not really make a clear point about whether ECA is related to soil texture or like soil water content or soil salinity. So what are we measuring when we use proximal ECA sensing remains to be the question. Also, there's a lacking of information on delineating vineyard into different zones to serve a variable rate management strategies with the hope of eventually minimizing these spatial variability. Thus, there are two objectives of this study. The first is to investigate whether proximal sensing of soil ECA may provide spatial information on soil-plant water relationships, and explain the spatial variability in grape and wine chemical composition. So we hypothesized that if spatial variability is present in soil and cultural practices are applied uniformly within a vineyard, which is the common case, the variability in soil ECA will mainly depend on soil moisture content. Further, the variability in soil moisture content will translate into variability in plant water status and plant physiology, barochemistry, so on. Second is to validate whether soil ECA sensing can provide direction in delineating a vineyard based on its relation with plant water status for all these variable rate management strategy we just mentioned. So we have two vineyards in this study. I'll start with the first one, which is located in our Oakville station. And this study was conducted in 2018 and 2019. The cultivar used in this study was Cabernet Sauvignon, grafted on 3309. The vineyard spacing was 1.5 meter by 2 meters, vine by row. The trellis is single high wire with bilateral quarter round. We irrigate the vineyard from fruit set to harvest with 50% ETC, and the canopy management was done with mechanical box pruning to 100 millimeters, which is about 4 inches, with no other canopy management. So to assess the soil spatial variability, EM38 was used to in both vertical mode and horizontal mode to assess two depth, including deep, which is from 0.75 to 1.5 meters deep, and shallow from 0 to 0.75 deep. And time domain reflectometry TDR sensors were installed at 4 experimental units. 3 TDR sensors were installed at 0.375 meters deep, 0.75, and 1.45 at each location to collect the soil measurement throughout the season. And all these data were analyzed by the R with all the geospatial analysis packages and ArcGIS. To ground truth the sensing, we assessed the soil samples in these 14 experimental units. It was like tough. And the leaf area index, leaf gas exchange, plant water status as midday stem water potential, yield components, berry composition were all recorded. At the same time, berry skin flavonols were also assessed. So I'll show the weather as the first part of the result. Between 2018 and 2019, the precipitation amounts were different. We had almost 3 times of rain in 2019 than 2018 during the dormant season. And the summer was dry as expected. The site only received 0.5 millimeters of rain in 2018 and 1.7 millimeters in 2019 during the study time from April to harvest, which is the late September and early October. As for growing degree day accumulation, the second season had 1,669 Celsius, slightly higher than 1,522 Celsius in the first season. So these 2 years were similar in growing degree days. And also for the first section of the results, I'll be presenting only the 2019 results, since it's the year we test the relationship between ECA and plant water status with all these soil parameters included. When we look at a soil texture in the deep soil layer, which is from 0.75 to 1.5 meters deep, there was higher clay and silt proportionally in the southwestern section of the vineyard. Conversely, the percentage of sand was lower in the same section. And in the shallow soil layer from 0 to 0.75 meters deep, the soil texture was relatively homogeneous compared to what was observed in the deep soil layer. There was only very small area in the northeastern section shows significant difference for clay and sand, where there was higher clay and lower sand comparing to the rest of the vineyard. And that was maybe just 1 or 2 data experimental unit in that area. So we can say in shallow soil, it's relatively homogeneous in soil texture. So soil ECA was continuously monitored throughout the whole season and showed a progressive decrease with time towards the harvest. So our assumption is the water is the main driver of the ECA. So it might be at this point. For deep soil, 52 days after bud break, DAB, as we call it, the northeastern section had lower ECA values. The same spatial pattern was evident at 94 DAB, although there was a smaller portion in the southeastern section of the vineyard having a relatively higher ECA. At 129 DAB, the spatial pattern observed previously became not evident. It was like everywhere. And at 166 DAB, when harvest started, the central section showed lower ECA comparing to the rest of the vineyard. For shallow soil, a small portion of the southwestern and northeastern section had lower ECA. At 94 DAB, lower ECA in the southwestern section was noticed, and 166 DAB lower ECA values or in the northwestern section of the vineyard compared to the rest of the vineyard. So we are trying to prove that the canopy was not a confounding factor affecting the soil plant water relations. So when we look at a leaf area index and then EVI in 2019, minimal variability can be noticed in both leaf area index and EVI. It was confirmed by chi-square test with a p-value of 0.11. Therefore, the canopy was not interfering with the soil plant water relationship. So it was not in a way. The plant water status was directly derived from the soil, and we can say that's our case. So a multivariate regression analysis was performed, and the model was fitted with these 6 soil parameters, including soil water content, clay, silt, soil organic content, gravel, and soil salinity as ECE here. And we got this equation in color red. Such model could provide a prediction of ECA from soil water content with R-square of 0.96, which is pretty good, and the p-value less than 0.0001. These soil parameters were considered in this model since they are relatively stable in the vineyard soils, and there was no need for recurring measurement except the soil organic matter maybe, and the soil salinity and the soil water content. Thus, they can make this model more representative and consistent when transferring soil water content to soil ECA or vice versa. When regressing the values of the ECA estimated with this model to the ECA values of measured in the field by EM38, an R-square of 0.58, a p-value of 0.0002, and a root mean square of error of root mean square error of 4.8 millisiemens per meter were obtained. So we can say these two things fit pretty well with each other by this model. And to investigate the relationship between ECA and soil water content with other soil characteristics included, when conducting the analysis of relative importance, we found that the soil water content contributed most significantly to soil ECA at about 24%, and following by the soil texture as the soil texture was the second contributor to soil ECA, including the silt with about 22% and the clay with about 18% relative contributions respectively. And the soil salinity, ECE, had the least contribution towards soil ECA among these 6 predictors with only 5.5%. This is because the study site is non-saline and has very low soil salinity, where the shallow soil ECE was lower than 2.5 decisiemens per meter for the whole season. So the assumption here is the salinity is not a confounding factor affecting the relationships either. So it's mainly the soil water content and soil texture driving these ECA values we can measure by EM38. So the season-long stem water potential and stomata conductance integrals were regressed and showed an R-square of 0.66 and p-value of 0.0004. The stem water potential and the stomata conductance are the two factors reflecting very well of the plant water status, and they are also interrelated in our case. So we can use these two to represent the plant water status in this study. Since this study has evaluated the relationship between the soil ECA and the soil characteristics, which can use soil ECA to explain the plant water availability or the plant water status. The linear relationships were investigated between ECA and plant water status expressed in the term of, like we mentioned, the stem water potential and stomata conductance to evaluate the existence of direct relationships. We noticed that the deep soil ECA was closely related to stem water potential with an R-square of 0.72 and p-value of 0.0038. However, the same relationship was not evident in the shallow soil layer. And a similar relationship was observed between the deep soil ECA and stomata conductance, like in the circle. We saw an R-square of 0.5 and a p-value of 0.02. However, the relationship between the ECA and the stomata, again, was not as close, as significant in the shallow soil layer. So the deep soil sensing can really give us the plant water status estimation. So to conclude the first section, the soil ECA measured with proximal sensing in the deep soil layer can be more closely related to plant water status. The soil water content and soil texture were the main main factors determining soil ECA in our case. Once the vineyard soil is surveyed and its texture is determined, the soil ECA can be used to infer variations in plant water status. And this might be more of a case or region related phenomenon. Some vineyards might be like saline or you have higher salinity, but my point here is you need to know your soil first. And so the soil proximal sensing can really be relevant and useful. Now we move on to the second section of the study. The same vineyard was delineated into two clusters by K-means clustering analysis on the interpolation maps from the stem water potential integrals, which is the long-term plant water status, so to speak. For each season, there were two zones generated, including a severely water stressed zone and the moderately water stressed zone. The severely water stressed zone is in color red, and the moderately water stressed zone is in color green. The separation described about 71% in 2018 and 68% in 2019 of the variability in the plant water status spatially. A clear pattern was evident in 2018, where most of the southwestern section showed more negative stem water potential values than the rest of the vineyard. In 2019, a larger area in the central section of the vineyard had more negative stem water potential values. Comparing the clusters of both years, there was a 73% similarity between the clustering map in the year 1 to the clustering map in the year 2. So the separation was fairly consistent in the vineyard from year 1 to year 2. Okay. So for soil ECA, here we have the soil ECA maps for 2018 and 2019 harvests. In 2018, ECA in deep soil was lower in the southwestern section, as well as the central little portion in the central section of the vineyard. Shallow soil showed lower ECA in the southwestern corner of the vineyard in 2018. However, ECA in deep soil were lower only in the central section, as we saw in the first section of this presentation. And a similar trend was evident in the shallow soil in 2019, as we saw in the first season, where lower ECA were measured in the southwestern section of the vineyard. As we saw in previous slides, the overall trend in long-term stem water potential maps was able to partially elucidate the trend seen in the soil ECA maps. So when comparing the stem water potential on each measurement day between the two zones, it showed that the two zones were consistently separated, where the severely water-stressed zone had more negative stem water potential. We also compared the leaf gas exchange data between the two zones, the separation in net carbon accumulation, which is on the top, between the two zones was evident on August 16th, 2018, August 15th, 2019, and August 29th, 2019, where the moderately water-stressed zone had greater net carbon accumulation. For stomata conductance, the moderately water-stressed zone had greater values in the early season of 2018. In 2019, the same patterns were observed in the early season as well. As for intrinsic water use efficiency, the water use efficiency was greater in the severe water stress zone in the early season of 2018. In 2019, water use efficiency was significantly higher in the severely water stress zone on August 1st and August 29th. But on August 15th, the moderately water stress zone had higher water use efficiency, but I think it was an exception. The yield components show very few differences because the severe stress, we call it severe stress, is not like biological severe for grapevines. So we didn't see that many differences between these two zones. So only berry weight and berry skin weight were greater in the moderately water stress zone in 2018. Although there was no difference between the two zones, cluster number per vine, cluster weight, and yield per vine were lower in the second season compared to the first, and leaf area to fruit ratio was higher in the second season. So there's a seasonal effect. Also, there was few differences between the two zones in berry primary metabolism. The two zones had the same berry juice, total soluble solids, tetrahedral acidity, and pH at harvest in both 2018 and 2019, except tetrahedral acidity was higher in the moderately water stress zone in 2019. However, when comparing year 1 to year 2, the year effect, remember, the fruits showed a more advanced maturity in 2019, although we picked them around the same time of the year, which was at the end of September. This might be due to the higher leaf area to fruit ratio in 2019 we saw in the previous slides. Between these two zones, the skin flavonols did not show many differences, except the total quercetin and total flavonols were higher in the severe water stress zone in 2019. And as for berry skin anthocyanins, purinidine 3-glucoside, malvidin 3-glucoside, and purinidine 3-glucoside coumarate were all higher in the moderately water stress zone than the severely water stress zone in 2018. In 2019, there was no difference between the two zones in any of these anthocyanin derivatives. So again, when investigating the relationships between soil ECA and plant water status, in 2018, there was a direct and positive relationship between the deep soil ECA and stem water potential integrals. And this deep soil ECA was only assessed on the harvest day. This is not a continuous measurement. but still we saw this correlation at the end of the season. A similar relationship was evident with shallow ECA, although the correlation was not as significant as deep soil EC with a p-value of 0.056. In 2019, deep soil ECA had a moderate correlation with stem water potential, and there was only a weak correlation between the shallow soil ECA and stem water potential intervals. These two correlations were not statistically significant. Overall, the soil ECA assessed on the days close to harvest was able to provide a simple and direct correlation with season-long plant water status, just like what we observed with the continuous measurement on ECA in the first section of this presentation. Similar with stem water potential intervals, the relationship between the ECA and the stomata conductance intervals showed a positive correlation between stomata conductance between these two parameters in 2018, particularly with deep ECA, where the correlation was significant with a p-value of 0.02. In 2019, deep soil ECA showed a similar trend with stomata conductance intervals. However, the relationship between them was not significant again. The shallow ECA was not related to stomata conductance intervals in the second season. So to conclude the second section, the differences in season-long plant water status affected the grapevine leaf photosynthesis, gas exchange, and the primary metabolism to a degree that they have some separations in some parameters, as we saw. Hence, the plant physiology altered by this plant water status. The variability assessed by soil ECA sensing can be related to long-term plant water status, which will be further observed in the berry development, as we saw between these two zones. And the plant water status can be used to delineate the vineyard, and it can be a plausible approach for further future variable rate management, like selective harvesting to pick the fruit at a different maturity or the same maturity differently. And this can maybe potentially minimize the spatial variability in this vineyard. So we move on to the third section of the study, which was actually done before the first two sections. It was conducted in Cabernet Sauvignon vineyard in Hillsborough, California, with 110R as the rootstock. The vineyard spacing was 1.83 meters by 3.35 meters, 1 by row, and the trellis was quadrilateral canopies with 2 bilateral cordons. We irrigate the vineyard at 50% of ETC from fruit set to harvest. And the canopy was spring pruned with 2 buds per spur and 7 buds per meter of the cordon. Again, the weather will be the first part of the results. The weather between these 2 years were similar. The only differences were observed in the precipitation amounts, where the amount in the dormant season prior to 2016 was about 560 millimeters. However, this amount was about 900 millimeters in the 2016 to 2017 dormant season. Summers were dry, of course. There were almost no precipitation from May to September. So the growing degree days were similar between the 2 years, with 2017 season being slightly higher with 1,220 Celsius comparing to 1,183 Celsius in 2016. And the accumulated ETO were higher in the second year, about 872 millimeters, comparing to the first season, 750 millimeters. Soil texture was measured at 2 different depths, deep and shallow, 0.75 to 1.5 and 0 to 0.75. In deep soil, the majority of the western section consists most of the loam, with a small portion of clay loam in the southwestern corner of the vineyard, with the remainder being characterized as sandy clay loam. In shallow soil, the eastern section mainly was sandy clay loam, with the rest of the vineyard having loam. So we had more clay and loam on the southwestern part of the vineyard, and we have more sand on the rest. As for soil ECA, in deep soil, ECA values were lower in the majority of the western section of the vineyard, or southwestern, if you want to say. In shallow soil, ECA values were lower in the northwestern section, northwestern corner of the vineyard, and a small portion of the central section also had a lower ECA. One thing to note is that there was no positive correlation between clay content, as we see between these four maps. And soil ECA observed in this study, the section had higher clay content, show lower soil bulk, soil ECA or bulk EC. Excuse me. These are the interpolation maps for plant water status as stem water potential intervals for both seasons. The vineyard then was delineated into two clusters by k-means clustering analysis. We got two clusters as before, one severely water-stressed zone and a moderately water-stressed zone. In 2016, k-means clustering explained about 99% of variability of the plant water status. And in 2017, k-means clustering explained about like 78% of the variability. The two clusters from year 1 to year 2 had about 85% similarity. In 2016, the clustering map was 65% and 73% similar to the deep soil and shallow soil texture maps, respectively. In 2017, the clustering map was, the two clustering maps were 70% and 78% similar to the deep soil and shallow soil texture maps, respectively. Like here, you see the similarity there. So based on the two clusters, the fruits were harvested differently and fermented separately. So we'll have the wine data here. So I'll be quick with the next few slides. What I'm trying to show here is that based on the vineyard delineation, these two zones perform differently in plant water status and gas exchange. We can see that in 2016, moderate water stress zone consistently had higher stem water potential, stomata conductance, and night carbon accumulation than severely water stress zone. And for intrinsic water use efficiency, it was lower in the moderately water stress zone. Same pattern was noticeable in the second season, where the moderately water stress zone consistently had higher stomata conductance, net carbon accumulation, and stem water potential than the severely water stress zone. Again, the intrinsic water use efficiency was lower in the severe water stress zone, but we had a like exception in this year. The August 24th showed higher values with in the severely water stress zone. These results led to differences in berry composition. At harvest, in moderately water stress zone, the berries were heavier at harvest, which is August 5th, 2018. The total soluble solids were higher in a severely water stress zone compared to the moderately water stress zone when pushing close to harvest. And in 2016, severely water stress zone reached about 30 bricks, which was high bricks, comparing to the 27 bricks in the other zone. pH was higher at harvest, and TA was consistently lower in severely water stress zone through the whole year. In 2017, berry weight was higher, again in moderately water stress zone at harvest. Again, total soluble solids were higher in severely water stress zone. From September to September 20th, when we harvest the fruits. But in 2017, the severely water-stressed zone was harvested when it reached 27 bricks comparing to 25 in the other zone. So we harvested these fruits a little bit earlier than we did in the first year. The pH and TA were behaving the same as the first season, with the pH higher in the severely water-stressed zone and the TA higher in the moderately water-stressed zone throughout the season. Between the two plant water status zones, there was no difference in yield, berry number, pruning weight, or reverse index. However, there was an effect of experimental year, again in this section, where we measure greater yield and lower pruning weight in year 2. The only difference observed in yield components was that the berry skin weight was greater in the severe water stress zone in the second year. Skin anthocyanins between the two zones, the first year showed most of the differences were observed. Moderate water stress zone showed higher values in every anthocyanin derivative and total anthocyanins at harvest. Conversely, in 2017, the total malodins, trihydroxylated anthocyanins, and total anthocyanins were higher in severe water stress zone at harvest. And the difference is partially translated into wines. For anthocyanins, moderately water stress zone had higher concentrations of all anthocyanin derivatives in 2016. All the compounds were more than 2 times greater in moderately water stress zone than severely water stress zone. However, there was no difference observed in any of these compounds in 2017. The overall concentrations of all these compounds were greater in 2017 than 2016. So we had a year effect here. For proanthocyanidins, which is the condensed tannins, similar results were observed. In 2016, all the extension and terminal subunits were higher in moderately water stress zone than severely water stress zone. The amount of total proanthocyanidins were also higher in moderately water stress zone. And there was no difference in mean degree of polymerization between the two zones. In 2017, however, there was no difference observed in any of these subunits or total proanthocyanidins as we saw in anthocyanins in the wine. Again, the second season showed a greater concentration in all of these compounds comparing to the first season. So again, we saw the year effect here in proanthocyanidin as well. To explain the discrepancy between the two seasons, the temporal relationships between the total soluble solids and the berry skin anthocyanins were investigated. In both years, skin anthocyanins increased with the accumulation of total soluble solids at first. In 2016, berry anthocyanins in the severely water stress zone had a significant decline after about 25 bricks, resulting in a lower concentration. So conversely, the second season consistently showed a greater anthocyanin concentration in the berry skins in the severely water stress zone than the moderately water stress zone. At harvest, the skin anthocyanins were also declining, but it was at a similar level comparing to the moderately water stress zone due to the early harvest time, as we harvested the severe water stress zone at 27 out of the 30 bricks from the first season. So we didn't wait that long. We didn't wait the degradation continue for a longer time. The relationships between soil ECA and the whole grapevine physiology were investigated. Soil ECA and stem water potential were significantly correlated in both seasons. And again, the correlations were, the relationships were positive. So when you have more ECA, higher ECA, you have higher plant water status. The relationships between soil ECA and total soluble solids was significant in both years, and it was negative. So when you have more water stress, you have higher total soluble solids, basically. In 2016, stem water potential showed a positive correlation with berry weight at harvest. No significant correlation was observed between soil ECA and berry weight. However, shallow soil ECA showed a positive correlation with berry weight besides stem water potential in 2017. In 2017, both berry skin weight and total anthocyanins were positively correlated with stem water potential, deep ECA and the shallow ECA. So it's more related to plant water status and soil EC. And to conclude, the last section of my presentation, soil bulk EC ECA in vineyard systems affected plant water status, where the positive relationship between the season-long water status and ECA were observed in our study. Soil texture showed a spatial similarity with ECA, but water content had a more direct effect on the values we can get from the proximal sensing for ECA. Vineyard zoning based on plant water status can be used to manage the vineyard to minimize the variability in berry and wine chemistry. And after the soil scrutinized, this is the point I'm going to make again. After the soil scrutinized, the soil proximal sensing for ECA can be used to derive the management zones, because it can be really linked to the plant water status and all these plant physiology development. So for future work, an assessment of general root depth should be performed to ensure the soil ECA captured are in the depth that most of the active roots are present, making the soil data assessed by proximal sensing more relevant towards plant growth and development. And with the soil being measured by proximal sensing, aerial imagery for vegetation indices or other canopy parameters can be integrated to complement plant water status assessment. And surface renewal can be integrated into the system as well with the soil TDR monitoring. By doing that, the vineyard water input and output can be thoroughly monitored and managed. Variable rate management can be tested if the technologies are available or accessible. Sampling models such as Vineyard and Stone, KNS, and surface response SR to generate all these smart points can be tested to minimize sampling points spatially in these large area vineyards. Also, we can test if the vineyard delineation can be done really directly by soil ECA sensing, if the relationships are connected and scrutinized. So I want to thank all these funding opportunities, and I want to thank you for your attention. 47 minutes, and that's it.
All right, thank you, Cliff. That was quite a presentation.
It's so quiet now.
Yeah, usually is.
Okay. Is there any question?
Any questions, everyone?
I have a question. This is Daniele.
Yeah, I know it's you.
And I think I asked you this question before we talked a little bit about it. So the EM38 feels some disturbance from the wires, from metals in the trellis system at the vineyard, right? And yeah. So to some extent, that's forced you to basically survey the central part of the interrow.
Yeah.
And this central part of the interrow somehow is feeling the, let me phrase this right. It's feeling the water distribution in the micro-irrigated vineyard. And this water distribution in the soil might be affected by the differences in soil texture. So what I'm trying to say is that by running this EM38 at the center of the interrow, you might have different signals because also the shape of the bulb, the wet bulb, might be affected by the soil water distribution. So somehow this is a confounding effect.
Yeah.
And I just want to ask you, if you have any idea how this could be somehow taken care of when you do this survey for multiple purposes that you described during this presentation.
Yeah, I think the wire is potentially being as a confounding factor, but as we saw in the first section, that with all these TDR sensors in the soil, which is like close to the vine roots, and the soil water content, all these correlation regressions still regress to the EM38 measurements. So that can give us some hope that the EM38 is capturing some of these, is capturing most of these soil water information, as even though we measure the soil ECA in the rows, because it's like it's not a single profile. It's measuring like a ball, like a 1.5 meters diameter of how to say, it's measuring all these all these areas around that. So it's still, you can get a lot of information out of the measurements. So, but that can be something to look into, because like I mentioned, also you're not only want to measure the soil under the vine, you want to really capture what's growing in the soil as the active root density. So you want to capture those distributions. So I think by the TDR sensors, we can get more details. And that's going to be in the third paper, I think.
Okay. So Cliff, just to remind me, the TDR sensor were installed, how close to the dripper?
I'm trying to avoid the dripper because
how far? Let's put it this way: how far from the emitters were installed?
I don't have an exact number, but I think it's more than like 40, 50 centimeters.
All right. Okay. All right. Thank you.
Thank you. Any other questions or comments?
I also have one question.
Okay.
In terms of developing a new vineyard, what is the most reliable date to scan the soils and create subzones for a new irrigation systems? Dry or wet soils are better?
I'm sorry, can you repeat the question? You were cutting out.
Yes. In terms to develop a new vineyard and also plannings to develop an irrigation system, what is the most reliable date in the season to scan the soils and create subzones that really reflects what's going to happen in the future? So you prefer to use dry soils or wet soils for the scanning?
Okay, so your question is when is a good time to do the soil survey?
Yes,
right?
In order to create a new vineyard, in order to develop, design an irrigation system for a new vineyard.
So a lot of people say at the field capacity because you have the soil filled by water. So when you measure it, you can measure the soil texture. So that can give you a lot of information because soil texture is not changing throughout the season. As we saw in the last section of this study,
Yes.
the soil texture is not really correlating. The correlation that these researchers saw in the previous studies, more clay means more bulk EC. We didn't see that. So to be safe, I think, yeah, at field scale, you do one survey, maybe at harvest, you do another one.
Okay, perfect.
Yeah.
Great, thank you.
Thank you. Lunchtime.
Cliff, this is Blake Sandin. Can you hear me?
Yeah, I can hear.
Yeah, I would just like a little clarification because at one point in your presentation, you provided a regression formula with everything from ECE to clay content to water content and a number of things. And you listed it as ECA equals all of these. And then you gave a really nice table that showed the percentage contribution of each of those items. And I found it interesting that, by far the water and the clay content were the number one contributors to the ECA signal. And so the clarification, well, I'd like two things. One, I'd like a copy of that table. That was a great table. Two, in your beginning maps, when you showed the very first part of the presentation, you showed a number of ECA maps at different number of days after bloom.
Yeah.
And the yellowest ECA map that you showed was the very first one. I don't know, 34 days after bloom, something like that. And so here's my question to you. Were those contour maps generated with your calculated ECA, which might be more appropriately called ECE/A, or were those contour maps of the direct conductance readings off the EM38? You listed the units as millisiemens per meter, which is, those guys.
Yeah.
Yeah. The shallow and the deep. You listed the units as millisiemens per meter, which is the default unit that the Geonics EM38 spits out. So are these maps just straight conductance readings, or are these the regression calculations you did?
Yeah, I got your question. So the first question, I'll send you the table. I'll send you the table for sure.
Cool.
And the second question is, these are from the EM38. These are the maps generated by the proximal sensing. So these are the real data we're measuring in the field, not by the regression.
Okay.
So
great. That's what I thought. Because as you showed with that with that nice table, the raw magnetic conductance readings off the EM38 fold in a whole bunch of parameters, salt water, soil texture, that provide a unique integrated reading that can help with overall water and salinity management. But in the end of the day, correct me if I'm wrong, the biggest take-home message out of your whole presentation is that in the end of the day, it's still the leaf water potential that provides us the most immediate management feedback for the stress level we want to keep on the grapes. Is that pretty much the take-home message after all your hard work?
Because I think we're still trying to connect these two things from soil to plant. So there's still a little gap there. So we don't want like make big assumptions like say, oh, EM38 is the device we can use to delineate our vineyard, because all these relationship we saw was like verified, but these are still the thing we need more details to complete. So we use plant water status because it's more directly directing our like plant physiology, biochemistry development. So we want to establish the first the relationship between the soil ECA and soil water content, maybe plant water status. As we saw in this study, it was like positive correlations, the line, and it was significant. And from there, maybe plant water status was affecting all these biochemistries, yada, yada, yada. And maybe in the future, we can say, oh, maybe this is a device we can use without question, that we can divide this vineyard into different zones. And we know for sure it can give us plant water status and biochemistry. But I think that will be the next step.
Okay, I hear another couple papers coming.
Yeah, definitely.
Yeah, we have quite a few in the pipeline. Well, anyways, I think we have finished our allotted time, and people have to go to other classes, although virtually. So I'd like to congratulate Cliff for sticking with this very long-winded project. I think he traveled close to 27,000 miles within the 4 years he was doing these projects. Between Davis and all around California, it was quite a trying experiment. So if there are no more questions and we're out of time, I'd like to congratulate Cliff and thank you for attending.
Congratulations, Cliff.
Yep.
Good job.
Thank you.
Yeah, now come back to work.
Congrats. Not bad.
Yeah, Blake, send me an email. Blake, please send me an email. I can send you the graph.
Okay, I have his email. I'll send it. All right.
Okay, okay.
Thank you.
All right. See you guys. Bye.
Bye. Have a good day.